I want to do a few final tests before the power supply gets mounted into the electronic load. See if I've missed anything. The first test I want to do is to see how well the power supply handles a large load change on the 12-volt rail. If I do end up switching the fans, this will be a common occurrence. So I have the load set to around 30 milliamps on the negative 5-volt rail, 50 milliamps on the 5-volt rail, 100 milliamps on the 3.3-volt rail, and 50 milliamps on the 12-volt rail. I'm going to use this as the baseline for the power draw without the fans running. Here, I go from a 50 milliamp load on the 12-volt rail to a 200 milliamp load. Channel 1 is the switch node, channel 2 is the 12-volt rail. Less than a 300 millivolt drop. I think that will be fine. The DC voltage on the 12-volt line goes from 12.81 volts to 12.69 volts. Of course, the other three rails go up by a few millivolts. And here's the switch from 200 milliamps to 50 milliamps on the 12-volt rail. Just under 300 millivolt overshoot. I don't think that's going to cause a problem. Maybe a tiny bit of instability here. The 12-volt rail has a 22 microfarad output capacitor and less than 2% ripple at 200 milliamps. Seems okay. I have lowered the load on the 12-volt rail to 30 milliamps. Here, the controller is entering hiccup mode, so I'm going to have to keep at least a 40 milliamp load on the 12-volt supply. It was doing these tests that I noticed a strange instability, and at first it seemed to be related to the input voltage to the power supply. Anything over about 20.4 volts would cause some oscillation in the output. But it turned out that if I changed the load up or down, the input voltage range that would cause the oscillation would change. First thing I did was add some capacitance to the outputs. Did not seem to make any difference. After the added capacitance didn't have any effect, I started looking at the switch node more closely. Channel 1 is the switch node, channel 3 is the 12-volt line. As I vary the input voltage, the duty cycle changes, as would be expected. The oscillations show up on the output voltage rails when the switch on time occurs close to a low point in the transformer's resonant waveform. That should be well after the error amp samples the reflective voltage, maybe why changing the output capacitance had no effect on it. The switch node waveform here I think looks pretty good. If I'm reading the datasheet correctly, the error amp sampling should be occurring toward the end of this portion of the waveform. So I don't think the ringing in the flyback pulse would be affecting it. But the ringing does last for around 400 nanoseconds, so I think I need to try and fix that. I'm going to give TI's Calculate an RC Snubber in 7 steps a try. It looks pretty straightforward. So first I need the ringing frequency with no snubber in place. Looks like the ringing is around 21 megahertz. Next step is to add a capacitor to the switch node. Needs to be several times larger than the switch node capacitance. Since the 220 picofarad snubber I had in place didn't quite cut the ringing frequency in half, I'll go a bit larger. So I've added a 330 picofarad to the switch node. And now it looks like this. Even though the cursor is not set, the ringing frequency is about 10.2 megahertz. So I have the three values I need: start frequency, end frequency, and capacitance value to get to end frequency. I'll put the values into an octave program, which makes the last 5 steps just one click. Then run it. So result is a 305 picofarad capacitor. I'll go with the 330. Snubber resistor is close to 75 ohms. I think the closest I have is 51 ohms, so I'll go with that. And here's the result. That looks very good. Much better than the 220 picofarad 33 ohm snubber I had in it. Sure would have been nice if that was the cause of the instability, but it wasn't. I am really at a loss to know which direction to head in, so I think I'll try shifting the switching frequency and see what effect it has. Here I've increased the frequency to about 135 kilohertz. And it seems to be about the same. Now going down to 100 kilohertz. Well, still does it some, but I will say it is better, quite a bit better. Does that mean the inductance of the transformer primary is too high? I can test that without touching the windings. I'm going to go back to the 123 kilohertz operating frequency, and I'm going to increase the gap in the core. I'll remove the hot glue holding the core top in place. The hot glue comes off quite easily. Too easy to rely on it to hold the core in place for the long term. I have a new core half with 6 layers of Kapton tape, in place of the 4 layers I had. Turns out you can't apply much pressure to the core half when the center is not supported. They are quite fragile. Lesson learned. Hot melt glue it in place. Now if my calculated inductance value is correct, this is going to be below the minimum value required, so let's see what happens. Okay, I'm at base load, 100 milliamps on 3.7 volts, 50 milliamps on the 5.7 volts, 30 milliamps on the negative 6.1 volts, and 50 milliamps on the 12.7 volts. Well, it's still doing it. I don't think it is as bad. This is with 40 milliamps on the 12 volt rail. It still goes down to 40 milliamps without going into hiccup mode, even with the inductance reduced. Here it is running at what I think will be full power. 30 milliamps on the negative 6.1 volts, 100 milliamps on the 5.7 volts, 200 milliamps on the 3.7 volt rail, and 300 milliamps on the 12.7 volt line. Still trying to do it a little bit, but it is better. Getting near the low voltage cutoff, probably the worst right here. Now getting near the overvoltage cutoff, strange that it doesn't seem unstable right near the overvoltage cutoff. I do find that strange. It may be that my primary inductance is much larger than I think. If anyone has any thoughts about this, I would appreciate any ideas to try. I want to get on with the main controller section, so I'm going to live with the power supply as it is for now. This is where I want to mount the power supply. I'm going to glue some small acrylic blocks in place, and these will line up with the 2 mounting holes in the power supply PC board. Tap a couple of holes for the mounting screws. Then use some 1/4-inch spacers and 3mm screws to attach the power supply. I'll drill a hole in the back for the power plug, and it's ready to try. Right now I don't have anything running off of the 3 lower supply rails, so I'm just putting a small dummy load on them. So with the fans running, voltages are running a bit high, but I'm leaving it like that for now. This will work for development of the main control board. It may not end up being the final power supply. Thank you for watching.